Alrighty, we're going to do an introduction to circular motion. This is the sort of second part to forces, and it ties in a lot to forces because circular motion requires forces to be acting, particularly a force that we'll talk about in a little bit. And yeah, it also has aspects of motion where we're going to look at velocity and acceleration, things from Unit 1. We're going to use Newton's law, second law rather, with sum of forces, mass, and acceleration. So lots of things to directly connect from Unit 2 forces, as well as a couple things from Unit 1 as far as velocity and changing velocity for acceleration. Okay, before we specifically write out and define what circular motion means, there's a common confusion point, or it often gets confused for one other type of motion. So it is different from something called rotational motion. So circular motion is what's happening here. We have an object. I'll go ahead and kind of shade in that object. So our object itself is traveling around in a circle, and we could draw an arrow to indicate maybe it's going this direction, like clockwise as it goes around and around and around. Now, it could be tied to a string where the string is here in the middle and it's being swung around on a string. It could be maybe a planet or moon in a circular orbit. There's a few different types of scenarios where we encounter circular motion. So we'll be exploring some of those as we continue through the video and then through some problems that we encounter. Now, rotational motion. So this here is like I've drawn a disc or a cylinder, and we could in unit 5 we'll talk about how we could imagine like an invisible line going right down through the middle of it, and then the whole thing, the entire object, like turns around that, almost like an invisible wire that's going through it. That's called rotational motion. When an object turns or rotates, and it rotates around that point or that line that like goes through the object itself, that's rotational motion. And we'll look at that later. That'll come in unit 5, but it's not circular motion, right? Circular motion is what we have here with the object going around and around in a circle. So what we're going to define it as is we're going to define it as the following. We're going to say circular motion is when an object moves in a circular path around some point that is outside the object itself. Around some point that is outside the object itself. We can go ahead and identify that point. There'd be some central point in the middle here, around which this object travels in a circle. Okay, so that's circular motion. We're going to eventually get to a more full description of this based on the forces that are acting. We'll talk about velocities and accelerations and kind of get a big picture of it. But there's your basics. There's just a basic visual on circular motion versus rotational. We're not going to do rotation in this unit. We're going to leave that for later. All right, so this object, as it goes around and around in a circle, it has kinematics values we could talk about, as in displacement. How far does it go as it goes around in a circle? And velocity, how fast is it going as it moves in its circular motion? Acceleration, is it speeding up, slowing down, changing direction as it goes? So we're going to start with displacement. Now, displacement, of course, previously we used delta x, delta y. So we had delta x horizontal, delta y vertical, measured in meters, using our big 5 equations to find those. Displacement still is how far it goes, But delta x, delta y actually don't really help us that much for this circular motion because if our object went once around the circle, in terms of delta x and delta y, it would actually be right back where it started horizontally and vertically, and we'd have 0y and 0x displacement. But we don't want to say that its displacement is just 0 if it did that in terms of horizontal vertical. Not only that, but if we're going left to right, it becomes a little harder to track. Like, okay, it goes to the left, to the right as it goes down in this circle here, and then it goes back to the left, and then it goes even more to the left when it goes over to the left side of the circle, and then it goes back to the right up at the top. So it's just sort of going back and forth left to right, and similarly, it's kind of going just back and forth up and down. It's like to the middle, and then the bottom, then back up. So this repetitive motion, it doesn't really help us to look at horizontal and vertical displacement. What we're going to do instead is we're going to define a new way to think about how far this goes. And we're going to describe it as basically how many times around the circle, or just how many times around, which still captures that idea of how far did we go. Okay. And then we'll ask some other questions. Let me fill in a little bit of some definitions for velocity and acceleration as well. So we'll kind of do this side by side. Velocity, sure, we do care about how fast it's going, but meters per second and our traditional way of finding velocity, we're not going to use meters per second here. What we're going to end up doing is we're going to talk about like essentially how many circles per second does the object complete. So that really is how fast it's going. If it goes once around in a second, okay, that's how fast it is. And then if it goes 2 circles in a second, that's even faster. If it goes only half of a circle in a second, that would be slower. So our velocity of how fast it's going, we can think of how many circles per second. And then acceleration is still just the same basic idea of does it speed up, slow down, or change direction. So we're bringing in some kinematics values. Displacement, we're not going to use a whole lot for circular motion. Velocity and acceleration, we will see a little more of those in our equations and in our problems and what we're doing. So acceleration is it speeding up or slowing down as it goes around? Kind of leaving some room here to fill in more information about displacement, velocity, acceleration for circular motion. Okay, so these are the questions we can answer to get our kinematics circular motion values. How many times around does it go? Is like how far is it going? How many circles per second? How fast does it go? And is it speeding up or slowing down as it goes around? Okay, so we're not going to use meters per second, or meters per second squared for measurements on this. What we're going to do instead is we're going to say the units of how many times around. There's a few ways we could think about this. We could do degrees and angles. We could say once around is 360. And then if you just keep going, you'd get up to like twice around is 720. But the problem with that is once you get to 3, 4, 5 times around, your numbers for an angle get really, really big. So we'd rather not say the displacement is 3,480 degrees. Instead, we're going to use, instead of degrees, we'll use radians, because degrees and radians both just help you understand or describe how far around a circle have we gone. 2 pi radians is of 360. That's one full time around a circle. Right? Hopefully you've seen this in some math classes where degrees and radians both can be used there. So pi radians would be half of a circle, 2 pi radians, one full circle, etc. Radians are just easier to deal with because that way, if you go around 50 times, you say, okay, 50 full circles is still just 100 pi radians because you've 2 pi is a full circle times 50 circles would be 100 pi radians. It's easier to work with those numbers and to deal with them than something like degrees. So our units are going to be radians, meaning if the displacement is this object went 1 full time around the circle, your displacement would be 2 pi radians. Velocity is going to be using radians per second. Which again is just like how many circles did it make? If it's 2 pi radians every second, that would be a full circle every second. If it's pi radians per second, it only goes half a circle in 1 second. So units are radians per second. And I think you're probably catching on here. Instead of meters, meters per second, and meters per second squared, we're using radians, radians per second, and radians per second squared. We could say acceleration is how every second that goes by, how many radians per second does the velocity change by as it speeds up or it slows down. Okay. And these are what we're going to call angular values. So we would technically say these are all angular displacement, velocity, acceleration. So I don't really have too much room to squeeze that in, but we'll try and we'll do it. We'll do it on the side here. Up here, we'll say these are all angular values. We're not going to throw that term around a ton. In this unit, we'll see a lot more with angular motion when we talk about rotation and stuff in Unit 5. So displacement, velocity, acceleration for a circle, we'd call them angular displacement, angular velocity, angular acceleration, right? Angle referring to angular, like going around a circle. We'll do the same thing with rotation. When things go around and around and around in rotation, we'll still have these angular values to fall back on of like how many times around does it go, how many times per or rotations or circles per second. Is it speeding up, slowing down as it goes around? Okay, so for circular motion, these are our kinematics values. We have some variables as well for all of them. So let's fill those in too. We use delta theta. So delta theta is just a change in angular position. So you could say you started a theta of 0, for example, and by the time you go halfway around the circle, your theta is pi radians. So your displacement would be final minus initial. So you would find the displacement by the change in angular position. Just like with the values from Unit 1, we'd say delta x is x final minus x initial, right? It's the final location or position minus the initial. You can do the exact same thing. So we could add in here also just the equation to find the most basic equation here is as follows. Delta theta, oops, got my delta theta equals theta final minus theta initial. All right, so if you started off and you were already half a circle through, you'd say, okay, our starting location, our position is pi radians because we've already gone half a circle, and then you go 2 more full circles beyond that. Now you're at what it'd be 3 pi over 2, 5 pi over 2, and you would do final minus initial, and you'd find that the displacement from pi radians to 5 pi over 2 radians would be 4 pi radians. Or I guess that would be 2. Yeah. Anyways, I'm trying to do the math in my head, but without numbers. So if you take the initial starting position in radians of how far it has gone from wherever it started, you can do final minus initial to find displacement. But normally we don't have to mess around with that. We're not really going to use this equation. We're just going to say, how many times around did it go? If it went around 4 times, well, that's 4 times 2 pi, so 8 pi radians of displacement. Velocity, very similarly, is just has a variable as well here. The vector, of course, because velocity has direction. And we're going to use a Greek letter omega. It's kind of like a W, but curved. you can use an equation for this that says if you want to find omega angular velocity, you can just do displacement over time, but we would do this. And that is importantly an average velocity. So average velocity equals displacement over time, just like it did from unit 1. All right, lastly, acceleration variable is alpha. Kind of looks like a fish. This is your Greek letter alpha, alpha for angular acceleration. And it also has a basic equation to work with. Acceleration is same as it was in unit 1. It's change in velocity over change in time. So really nothing has changed in terms of the basic understanding of what displacement, velocity, and acceleration are. They're still just, well, how far did it go? How many times around? How fast is it going? How many circles per second? And is it speeding up, slowing down, or changing direction? Even those equations of average velocity being displacement over time, or acceleration of how much it speeds up or slows down being the change in velocity over time, those are just carried over from unit 1. So the concept or idea of these things is the same. We're just adjusting sort of our units and our variables to describe it angularly going around and around instead of all the horizontal, vertical displacements we had for delta x, delta y, etc. in unit 1. Now, it is important to know these, like to be introduced to the kinematics values for circular motion, but we're not going to do a ton of kinematics. The primary use of these is for other things involving like Newton's second law and summing forces, and we'll have some other unique equations specifically for circular motion that we'll use, but we're not going to do a whole lot of kinematics. Now, one last thing to mention with all of these is direction. So for all three of these, they have a unique or different direction. We wouldn't say up, down, left, right. Direction is either clockwise or counterclockwise. So all of these, displacement, velocity, and acceleration, all of these have a direction that is clockwise or counterclockwise. So you could define, and one option with this would be you could draw like your normal thing. We could say like up is positive. We could say right is positive. And then we could draw one more thing here to say, I'm going to choose clockwise as positive. And that'd be a full description of all the directions you're choosing to say, well, if I was doing delta x, delta y, I'm going to choose up as positive. I'm going to choose right as positive. And if I'm doing circular motion, you could choose clockwise direction to be positive, counterclockwise negative. But that's the direction on these, right? If your object goes twice around the circle clockwise, you could say that displacement is positive 2 pi or 4 pi, twice around, positive 4 pi radians. Likewise, if your velocity is going counterclockwise and it goes half a circle every second, you could say negative pi radians per second is your velocity, your angular velocity. So, the direction is, and same thing holds with velocity and acceleration. If you're going around clockwise with a velocity that's clockwise, but your acceleration were counterclockwise, that would slow it down. If your acceleration and velocity are both clockwise, that would speed up. So same deal with if velocity and acceleration are the same direction, object speeds up. If the velocity and acceleration are opposite directions to each other, then the object will slow down. Okay, but that's your basics of this. Now, one thing to mention as far as Big Five equations is that Big Five still work here. We can use the exact same Big Five equations, simply substituting these angular values. I'll write a quick example here. We'll do number 3 because that's a common one. So we'd say delta theta displacement equals initial velocity omega 0 times t. You'll notice t is still just the same. Time is unchanged there. plus 1/2 times acceleration alpha times t squared. That would be big 5, number 3, instead of delta x, delta y, or initial velocity x or y, instead of acceleration x or y, we just replace those with the angular values. So displacement delta theta equals initial velocity times time plus 1/2 acceleration time squared. You won't really be doing a lot of this here in unit 2, but it might come up occasionally, and I think later on in like unit 5 we might see a little more of it too, actually using kinematics equations to look at, well, if it starts at 0 and it experiences this amount of acceleration for this long and this amount of time, how far does it go and what's its displacement? Things like that we could absolutely solve for, just like we did in unit 1. Okay, so that's the basics of kinematics for angular motion or circular motion. So just as a review, right, we want to know how many times around the circle did it go? That's displacement. How many circles per second? Velocity. Is it speeding up or slowing down as it goes around? Our units are radians, radians per second, and radians per second squared. We use these variables for angular displacement, velocity, and acceleration. Those variables are delta theta, omega, and alpha. And we use clockwise or counterclockwise as directions. Now, in this unit, we're going to see the most of, well, a couple of them. We're going to see probably omega the most, but also we're going to see alpha a decent amount. Alpha comes up more in like unit 5 when we get to torque and rotation, but we'll see that. We'll see it on occasion. The acceleration of an object in circular motion as far as alpha is concerned, we'll end up looking at a different acceleration, funny enough, but alpha we just don't do a whole lot with. So omega is kind of the main one that we'll see. Even then, it doesn't dominate the vast majority of problems or anything like that. These are just sort of a basic understanding that's going to help us out later when we do rotation and provides some variables that we are going to see here and there in a couple equations. Okay, so let's go back to what's actually going on with circular motion. I'm going to draw on the image that I already had here. So we of course could draw these arrows to indicate these velocity, acceleration. Like this one, we could say, it has a velocity. We can indicate omega like that, which is fine. You can absolutely do that if you want. But most of that's pretty self-explanatory, right? You could draw a curved arrow clockwise for omega if its velocity is clockwise. You could do the same thing for displacement. You could even draw like how far exactly does it go? If it goes halfway around the circle, you could draw your displacement, something like that. But it's especially once you go 2 or 3 or 4 or 5 times around, you don't really want to draw that displacement around and around and around, or otherwise you're just making a bunch of circles. So what we are going to draw on here and look at is, it turns out these objects have not only an angular velocity, displacement, acceleration, they actually, as they're going around in a circle, they also have a linear velocity. So let's talk through that and talk about what we mean by that. So right now, and I'm going to go ahead and draw like a string or something. So we'll draw something attaching this object to the center so that it's like on a string and we're like swinging it around in a circle. Draw my string a little more straight to the center. Okay. And now if we were to, at this exact spot, if we were to cut the string, this would be more like a slingshot kind of an idea. If we swing it around and around and around, and then we cut the string or release it from circular motion, what's going to happen is it's going to fly off in a straight line. Now it might become a projectile, and gravity would act on it, and it would like arc to the ground as a projectile because of gravity. But at a basic level, it's going to fly off in a straight line if we release it, and that straight line would look something like this. Get my direction right here. That's the way it would go, because it's going around clockwise, and if we cut the string or release it at exactly that point, it's going to fly off. Now, some of you from math situations might immediately recognize that line or arrow for the velocity that the object would have. You might recognize that as tangent to the circle. So this particular velocity, and it's not only if you cut the string. It turns out even if you haven't cut the string and it's still spinning around and around and around, it still has that exact linear velocity at that moment in time. And if it were allowed to, this is kind of like inertia with Newton's first law. Objects in motion will stay in motion. If it's got this velocity, it really is going to just keep going with that velocity until acted on by an unbalanced outside force, and then something can change with the motion of the object. And we'll observe that in just a second. So we call this velocity tangential velocity. We use a subscript t, vt. This is tangential velocity. And we're going to look at what happens to this tangential velocity um, as it goes around. Again, I like to think of this as what would happen to the object, or what would it do, right? What would the velocity look like if we suddenly released it from circular motion? Because it has this velocity as it goes around. The velocity is there. It is moving in that exact direction. And it turns out if we just allow it to keep doing that by cutting the string and letting it fly off, it'll go in that direction with the tangential velocity. Okay. So the reason that circular motion occurs is we're not allowing the object to keep going in that straight line with the tangential velocity and just fly off in that direction. Instead, the direction of that velocity is about to change as we continue through circular motion. So I'm going to pick a point a little bit later on the circle. We'll just go to like right here. And by this point in time, if we keep the string on there, we keep it attached, we keep turning it around, the object is going to have a tangential velocity that would look a little more like this. It's going to be more this direction. So that would be your VT. So as circular motion occurs, what happens is the direction of the tangential velocity changes. Now, an interesting thing about acceleration from Unit 1, when we defined it, we said, well, to accelerate, you could speed up, you could slow down, or you could change direction. Because velocity is a vector, and we're going to summarize all this. I'm doing a lot of setup. We'll write a full written description of what's going on with circular motion and the direction of this velocity changing, etc. But I just want to talk through velocity is a vector. And so if the direction changes, your vector is different. 20 miles an hour northeast is different from 20 miles an hour north because you turned. The magnitude of your vector might be the same, but your direction is different. You have a different vector. You've changed that vector, changed the velocity. So this is a change in velocity. Okay, so the object has this tangential velocity, and the circular motion is occurring because the direction of this velocity is changing all the time. If we go a little bit later, it's going to change again, right? If we pick another spot, now the tangential velocity is more like this. So at every single point along the circle, every spot that it goes, that velocity is changing direction a little bit more and more, and so that then it goes around in a circle. So what causes this to happen? Well, the only way that velocity changes is acceleration. If your velocity maintains constant, doesn't change magnitude, doesn't change direction, doesn't speed up, slow down, or change direction, then you would have constant velocity and no acceleration. But because our velocity's direction is changing, we must then have an acceleration. So let's look at that. Now, there's multiple ways that the direct acceleration could act. I'll note a couple that if we had an acceleration like this, what would happen there is your object would actually slow down. VT we'd draw a smaller arrow, then as the arrow decreases, it would slow down. It wouldn't be going as fast. That would be like alpha. That would be slowing down with an acceleration as it doesn't complete as many circles per second if your acceleration was that way. You could also have an acceleration like this. That would speed it up if it's in the same direction. So there's options of what your acceleration could look like to speed up or slow down the velocity, but neither of those is happening. It's not speeding up, it's not slowing down as it goes around in a circle. There are ways that can happen, and we'll look at a couple cases where there is some acceleration alpha or some acceleration that increases or decreases the magnitude of tangential velocity, making it go faster or slower. But for now, we're just changing the direction. And to go from the top purple arrow to the next one to go from almost straight to the right here to a little bit downwards and to the right. The acceleration that causes that to happen is an acceleration that is directly towards the center of the circle. So this is the acceleration that our object experiences in order to change the direction of the tangential velocity. It's an acceleration that acts directly towards the center of the circle. So this is called a C, subscript C, and this is a centripetal acceleration. Okay, so because the direction of the velocity is changing, there's an acceleration that acts directly inwards. This is called the centripetal acceleration AC. That's what changes the direction of the velocity. That's what keeps this object in circular motion. If that acceleration wasn't there, if there wasn't acceleration in that direction, the object would just keep going, right? That's Newton's first law. If it has a velocity and it's going in a certain direction, unless you put an unbalanced force on it to accelerate it, it's just going to keep going in that direction. So the reason circular motion occurs is that something causes that acceleration inwards. Okay, last step. What really causes the acceleration to happen? What causes the velocity to change the direction? What is causing this change in motion? That was back to our essential question for Unit 2. What causes changes in motion? Our general answer was forces, and it's going to be no different here. All right, so what really causes this, and the reason for centripetal acceleration, is a net force, right? Because we know from Newton's second law, if there's an unbalanced force in a certain direction, if there's a net force, we call it, when we do the sum of forces and find out, hey, there's, 5 newtons of net force acting in this direction, well, then there will be an acceleration because a net force is equal to a mass times acceleration. And we'll introduce that Newton's second law in just a little bit here. Okay, so there's a force acting, and that force is acting also inwards. Now, we could probably identify based on the string situation that this would be a force of tension in this case. But I'm not going to label this as a force of tension yet, because it turns out it's not always tension. Sure, you could have a string and swing an object in a circle on a string, but you could also have a planet orbiting a sun that's in a circular orbit, although that's not very common. We don't really see that. Usually they're elliptical orbits. But anyway, satellites could have a more or less circular orbit around the Earth. You could also have like other examples, like a loop-de-loop on a roller coaster as the object goes around. We could have like a washing machine could be an example of your clothes going around and around in a circle. So it's not all of those things. In fact, none of the other things I mentioned have a string or rope. So it's not always tension acting inwards to provide this acceleration. But in this particular case with a string or rope, it is a force of tension that pulls inwards. Okay, so we're going to call this FC. A centripetal force is a force that acts inwards directly towards the center of the circular motion. That inward force is centripetal. Now, one important thing to note, this is not its own unique type of force. It's not like applied force or gravity, right? Applied force is a person pushing or pulling or an animal. Gravity is the earth or another massive object pulling on something else with gravity. Friction is something sliding on a table or floor or maybe it's stationary with static friction. So centripetal force is not like that. Centripetal force is not its own type of force provided by a specific scenario like being in contact with a surface. Centripetal force is, well, it could be provided by this inward force, could be the result of something like tension in the case of a string. We'll look at force of gravity providing centripetal force for orbits. We'll see a normal force doing this for like a roller coaster going around a loop. We'll even see some friction in some cases, force of friction. Static friction is the big one there. We'll see like a something like a coin sitting on a merry-go-round. If you place a quarter or a nickel onto a merry-go-round and it sits there on the merry-go-round going around and around, then that coin itself is in circular motion around the middle of the merry-go-round. And the thing that keeps it going around and around is there is an inward force, which would be static friction between the object and the surface of the merry-go-round. So we'll see lots of scenarios where it could be a rope or string with tension. It could be gravitational force with orbits later on towards the end of Unit 2. We'll see normal forces providing that inward force. And sometimes it's a combination of multiple things. So what we're actually going to identify this as is the sum of all forces acting in the either in or out direction. Because if there happens to be tension pulling inwards and also gravity, because we didn't introduce or mention that here, but if this is we'll talk about vertical circles. If you swing something around in a vertical circle, gravity could be a factor here where gravity's acting on the object. And at the point we've drawn right up here at the top of the circle, not only would tension be pulling inwards, but gravity is also acting on the object straight downwards, which would be inwards at this point. So we'd have to figure out, well, how much is tension pulling inwards, and also how much is gravity acting with a force inwards. So that sum of forces in the in-out direction, that is what we mean by centripetal force. Once you add up all the forces acting directly in or directly outward away from the center of the circle, acting on the object, that's your centripetal force. And that net force, once you've added everything up, it will be inward. Because we need an inward force to provide that inward centripetal acceleration so that our velocity will change direction. And I'm not going to draw all the arrows because I ran a bit out of room, but if you went a little bit later, like here, you'd see also, once again, an inward force, like perpendicular to that tangential velocity, directed exactly inwards, providing the acceleration to change the velocity again and make it go more this direction. And then the velocity changes again, and those changes in the direction of velocity result in circular motion. Okay. Let's summarize. So I'm going to write this down here. I drew the picture all up there. So to fully summarize with our knowledge of now the forces that are acting, so there has to be that force. There must be a force inwards which provides that acceleration. So we'll say, to summarize, circular motion is when an object's tangential velocity continues to change direction due to a centripetal acceleration which is caused by a net inward. Again, there could be outward forces acting, but the net force, once you've added them all up, will be inward, a net inward centripetal force. So that's what causes circular motion to happen. When a force, like tension in the swinging an object on a string or rope example, a force acts inwards, or multiple forces could be acting, but the net force is inwards, centripetal force. That causes a centripetal acceleration, because whenever we have an unbalanced net force, acceleration results from that. That is Newton's second law, right? Sum of forces equals mass times acceleration. And when that acceleration acts inwards, it's going to change the direction of the tangential velocity, causing that object to keep going in a circle. Okay. Let's introduce some equations. So there's three main ones. The first one is really just Newton's second law of motion. It says, so for our circular motion equations, first one is Newton's second law of motion. So it says the sum of all forces acting inwards or outwards is equal to the centripetal force. And that is mass times centripetal acceleration. Because the sum of forces directly inwards or directly outwards from the towards the center of the circle or away from it, that sum of forces is centripetal force equal to mass times centripetal acceleration. So it is just Newton's second law. It's F equals ma, just circular motion version, right? That's the first of our circular motion equations. So that's number one. Number two, and I'm not going to talk really too much about where these come from. There's ways you could get to or derive these equations. This one is a way to look at centripetal acceleration, and it's equal to Vt squared over r. Just a heads up, this is simply the radius of your circular motion. How far is it from that central point that the object's going around out to the object itself? So radius of circular motion would be r. Okay, so that tells you that if you're going really, really fast, if your tangential velocity is huge and it's going super speedy, or if you have a really, really small radius of circular motion, both of those things are going to make your acceleration very large. If you want to spin something really fast in a circle, you're going to need a lot of acceleration and a lot of force to do that. If you want to spin something in a really tight circle with a small radius, if you make r really small, that's also going to make the acceleration very, very large. And you're going to need a lot of force to do that. Versus if you go really slowly and you have a super small tangential velocity vt, that will decrease your acceleration. Or if you get a bigger radius of circular motion, that would be another way to do it. So this one helps you look at centripetal acceleration, tangential velocity, and the radius of circular motion. So very, very handy equation. We'll definitely be using that one a lot. The third one we don't see quite as much, but it's basically a way to convert between tangential velocity and omega, actually, because you'll notice these are all linear values. So just a quick note of AC and VT are linear velocity and acceleration. These are not delta, theta, omega, and alpha. They're not the new ones we introduced. So this is meters per second squared, and this is meters per second. But now we're going to go back to omega. There's the radians per second showing up times r. So what this last one allows us to do is it allows us to convert between how many radians per second, like how many circles per second is this object going around and around and around, converting that to VT to say, well, if I were to release it, if I cut the string or let it go and it flies off in a straight line, what would be the linear velocity in meters per second that it would fly off with in that straight line? And of course, acceleration AC is linear because it's directly towards the center of the circle. There's no clockwise, counterclockwise there, right? VT is a linear velocity where if you allow it to escape from circular motion or just keep going, the object continues in that straight line with the linear velocity. And acceleration, centripetal acceleration, is linear because it's directly towards the center of the circle. And those are our equations. So they're pretty useful. We'll see them from time to time. Funny enough, we tend to use them in pairs or even all three of them. Like 1 and 2 together, you could, for example, find what's going on with the forces. So you figure out all your forces and your sum of forces. You get centripetal force and you know the mass. So now you find acceleration. But maybe the problem ultimately wants you to get tangential velocity. So now you take that acceleration that you know and you put it into the second equation. And if you know the radius, now you solve for tangential velocity. So they go together pretty well because the connection between 1 and 2 is acceleration. The connection between 2 and 3 is tangential velocity. And r, they both have r in them as well for 2 and 3. So a lot of times you will see 2 or even 3 of these equations used for the same particular problem. So we'll be doing that a fair amount. Okay. Cool. So that kind of summarizes like the basics of what circular motion looks like. There's all the kind of aspects of it here. So the aspects of circular motion, or the values here being tangential velocity. If we were to cut the string, or even if we don't cut the string, the object still has this velocity. It's just that if we don't release it and we keep it going in circular motion, this velocity will then change direction because there's a force acting inwards, causing that acceleration inwards, which changes the direction of this velocity to be a little more downwards at a slightly later point in time. And yeah, that change in velocity is what results in the circular motion. All right. Cool. Well, that's the basics of circular motion. Now, there's much more to say, like in class, through problems, through maybe looking at some more just examples. We might do some additional notes and things. We might talk about specifically like vertical circles. We'll either do that with problems and examples, or we'll just go through some more notes on that. So there's a few other things like which force is providing centripetal, because it could be tension, like the string example. It could be gravity when we get to orbits. It could be normal force for um, something going around a loop. We might even do a little bit with like banked curves, although that doesn't come up a whole lot for AP Physics 1. Okay, so circular motion can be a weird one. It can be like kind of tough to figure out. Like, okay, most people will get the idea that yeah, I can get the idea of an object going in a circle, like it's on a string or something, or it's just going around and around for whatever reason. But to really kind of grasp the idea of tangential velocity, well, what is that? It's not flying off in a straight line unless we let it, unless we release it from circular motion, but it still has this velocity, and that velocity then changes direction as it goes around. And the reason it changes direction is because there is an acceleration changing that velocity, which is acting inwards. And the force that provides that acceleration and causes it is also inwards, centripetal force. So yeah, it's just kind of a lot to put together. And um, yeah. So good questions are welcome, and questions of any type, right? Any question's a good question. So if you have something you're kind of wondering about with centripetal acceleration, force, tangential velocity, circular motion, kind of the basics of how this goes, definitely drop a question in the Padlet link on Schoology, or bring one to class, or just ask me on your own when you have a chance. Yeah, there's the basics of circular motion and kind of how it works, right? So as is often the case with physics, it feels a little more complicated than like, oh, something goes around in a circle. Well, we want to know why, we want to know what's happening, we want to know things like how fast is it going? Not only the omega, like how many circles per second will it complete as it goes around, but then specifically the linear tangential velocity of how fast is it going, like in a straight line direction at this exact moment in time, but then that direction changes as it keeps going in the circle. Okay. Yeah, we'll be doing problems involving forces like tension or normal force or even static friction providing centripetal force. We'll use the equations to deal with centripetal acceleration and tangential velocity. We'll look at the radius of circular motion for those as well. All right. Well, I guess that'll wrap it up for this video. So we'll see y'all in class, and we'll get to work on some of these problems.